welcome to another lecture of quantum mechanics. Now, this is a very basic question which was asked in BHU 2016 that it says that the de Broglie wavelength associated with 2 electron volt for photon and electron. See, both photon has energy 2 electron volt and electron has energy 2 electron volt. So it asks that what are the de Broglie wavelengths, right? So now let's start with this thing that the energy, the solution is like the energy of the rest mass energy. We know that of an electron, okay, so it's of the order of 511 keV. All right, so and the electron energy here is given to be 2 electron volt. So we can see that this energy is very less than, like, this is of the order of kilovolt, this is of the order of electron volt. Okay, this is 1000 times bigger than this. So here we need to do, the calculation should be what? See, we have already seen this, the energy is very less than m0c square, the kinetic energy, because there is no potential here. So we are talking just purely the kinetic energy is there. Okay, so it's very less than, so this calls for a non-relativistic formula. Okay, this calls for a non-relativistic formula. Now, this saying that lambda electron, the de Broglie wavelength is h by p. Okay, so this is equal to h by root 2m e. Okay, we had used this formula. Okay, in the previous part. So the value is 626 into 10 to the minus 34 joules second, and in root we have this 2 into 9.1. The mass of electron is 9.1 into 10 to the minus 31 kilogram, and this is 1.6 the electron volt. We are changing the value of electron volt, like it was 2 electron volt, so 2 into 1.6 into 10 to the minus 19 joules. Okay, this comes out to be around now this energy comes out to be around, the wavelength comes out to be around 1 point this thing, and this does not match with the question here. Now this is a problem, I must say, with the BHU question paper, that there are errors in it. Okay, so never mind, you just see whether you have the calculation we have done is correct or not. Now for the calculation of this photon part, you remember this easier to do calculation. This is approximately taken to be 124. This Planck constant multiplied by the speed of light gives you electron volt nanometer. Okay, so this is I think you should remember, for the exam point of view, it's very easier if you plug in this formula, like this result, you get the answer easily. Okay, so the de Broglie wavelength of photon is given by the hc by the energy of the photon. Now hc is given to be 1240 electron volt nanometer. Now nanometer, 1 nanometer is how much? This is 10 to the power minus 9 meters. Okay, so remember that. So electron volt. So this gives you the result. See, this is very easy to see. The EV gets cancelled here. Okay, and then you have this, you're left with the numerical value, which is 620 nanometer, or you can write down this is 200 angstrom. You know, angstrom is 1 angstrom is how much? This is 10 to the minus 10 meter. All right, so so you have to be careful. Okay, you have to be careful that to see. So this is not exactly, this does not exactly match with this thing. Okay, so I just missed on that. Actually, it's very close to this 9 angstrom, so we can obviously choose this thing. Sorry to say it was not a mistake, but like it's a very approximate value we have here. Okay, so this is 8.7 angstrom. This is very close to 9 angstrom, and this is 6200 angstrom. So this is the correct answer. Okay, this correct option is C. But there are you can, as we go on, we'll see that there are mistakes in some mistakes in the questions. Okay, so you have to be very careful while attempting the questions. Okay, so we'll discuss another question. So this is a very interesting question from which was asked in IITJAM 2016. This is a numerical based question in which we have to just answer using the numerical value, whichever the format is given. Now see, the student make a mistake when they learn something. Just try to plug in the formula. See, plugging in the formula doesn't solve your purpose. Okay, first try read the question and then try to answer it accordingly. The question says the de Broglie wavelength of the relativistic electron. It's already given it to it. You don't need to make a comparison. Although if you see the energy value here and this energy value, this is very good. This is almost of the order of the greater than this value, just mass energy. So we can safely, even if it was not mentioned here, that it is relativistic, we could have easily seen the energy and compared that this energy is almost the energy of the particle. Right, let's start with in this thing. If this was not mentioned, so relativistic was not mentioned, the energy here is 1 MeV. So this energy is almost of the order of the rest mass energy, which is 0.5 MeV. All right. So it's since I already mentioned, we don't need to worry about it. So what we need to do is we need the de Broglie wavelength, which is h by p, and this p has to be relativistic calculation. This p should come from relativistic calculation. Now, from how are energy and this thing is related momentum? Just look at the video which we had made for the relativity, which had contained the relativity formula. Just look at it. Okay, so what you do is you just you have this relationship. Okay, E, this is p square c square m naught square c4. Now just rearrange this thing. Okay, rearrange this thing. You'll get p is equal to, this is e square minus m naught c4 divided by c square. Okay, or this is 1 by c root over e square minus m naught c4. Okay, so in this case you have energy, you have rest mass energy, and you get the momentum. So plug in the values. Okay, if you plug in the values, what you get is 1 by c. Okay, let's come directly write down the lambda. So this is h by, instead of p, we'll write down h by, this is 1 by c root over e square minus m naught square c4. So this is hc by root over e naught square m naught c4. Okay, so what is happening here? So what we just plug in the values here. Hc, we already know that we had written this value. This is very easy to remember. 1240 eV nanometer. If you plug in here, what do you find out? That this is 1240 EV nanometer divided by this is 0.5 MeV. This is 1 MeV. So squaring this will get, yeah, I'm taking out outside the root. This will give you 6 again. Okay, 10 to the power 6. We are converted into electron volt. Okay, so this is 0.25, which is 0.5, the square of the like this 0.5. Okay, this is what? This is simply m naught c square whole square. Okay, which was 0.5. You just square 0.5, will get 0.25, and again it was in MeV. So you're squaring MeV and again taking a root, so it will remain in MeV. Okay, so what you get is 1240 into 10 to the power minus 9. This is in meter. All right, EV gets cancelled. We're writing it in mind. This will be 0.8860 into 10 to the power 6. Okay, and this value will be around 1.43 into 10 to the power minus 12 meter. So the answer here will be 1.43. Okay, this is a numerical value, so the answer the answer key would have been in the form of range, but this is correct, right? So this is how you solve it. First, the main objective for this kind of question is you need to find out how will you calculate the momentum and which calculation is required, relativistic or non-relativistic. Okay, and accordingly you need to plug in the formula. You don't start with the formula and then get into the problem. First, understand the problem, what are the requirements, what are the values given, and how can you calculate it. Okay, and see, you just saw that this formula is very useful. This result is very useful in the calculations. Okay, so try to follow the thing. Whenever I start with the problem, pause the video, do the problem, and then look at the solution. If you are able to get the answer, then you have understood the material. If you have not, just go through the previous videos, lectures, and see, you do not get the concept at once. You need to go revisit it several times before you get the hang of it. Okay, so before it becomes intuitive. Okay, for many of you it will be very intuitive, but for some of you might find it difficult in the first place. So what you need is to repeat it. Okay, it's like using a map to reach somewhere. Okay, so when you go for the first time, if you want to go to from A to B place, you ask people around, okay, how to go, like where to take a left, how to move from one place to another. You just keep on asking people. But once you reach B, then again you when you go there regularly, you don't need to ask anyone. You can just simply आप सिंपली क्या करते हो, आप सिंपली चले जाते हो. जैसे आप सिंपल मेट्रो एग्जांपल ले लो, दिल्ली मेट्रो या मेट्रो बहुत भी और भी जगह हो गए हैं. In the metro trains running, you when you go in a metro from one place to another place, you do not know, like you keep asking, you see the map, you like keep referring to signboards and everything. But once you start going there regularly, you can actually get the hang, like you, it becomes intuitive to you. You don't need to see the signboards. You just simply calculate which bogie, which compartment will have a lesser crowd, which place to stand, which if you stand in a certain compartment, which this staircase will be nearer to you. So it's very convenient for you. Your brain does all the work. Okay, so in this case also, in physics also, you need to keep on revisiting the concept, refer to different materials, not just one book. See, quantum, you need to refer at least 2-3 books to get to that. Like I've been referring to so many books for my lectures. All right, so some authors make an interpretation which is like somebody can understand, but someone doesn't understand that. Like somebody has to refer to more materials. The quantum is a difficult topic to understand, so you need to give it some time. You spend some time, you'll slowly get the hang of it. All right, so moving on to next problem. So calculate the question is, I'll just tell you the calculate uh, de Broglie wavelength for the following cases. Okay, first one is a ball of mass mass 100 gram and moving with 10 meter per second, moving at 10 meter per second. And another system which is an electron moving at speed 10 to the power 6 meter per second. Okay, so calculate these two and pause the video, try to solve it. Okay, and just see like which formulas to plug in and solve it. Okay, so I hope you have tried you paused the video and tried it. So let's go for the solution. So if you want to find out the de Broglie wavelength of the ball, which is h by p. Now this is of course a non-relativistic formula. So h is 6.26 10 to the power minus 34 divided by, this is a mass in kilogram into velocity, okay, in meter per second. So this is approximately 6.26626 10 to the power minus 34 meter. All right, and similarly, if we calculate the de Broglie wavelength of the electron, see in this case the speed is in 10 to the power 6, which is 100 times less than 100th of speed of light. So we can safely use non-relativistic formula. Okay, in this v is c by 100, almost c by 100. So in this case we'll use non-relativistic formula. Okay, so in this case this is 6.626 into 10 to the power minus 34. This is divided by, this is 9 point, the mass into velocity, right? So 31 into 10 to the power 6. Okay, so this gives you approximately 7.28 into 10 to the power this is around 10, right? So what we can conclude from here, now this is for the electron. Okay, so we know that the size of atom is of the order of 10 to the power minus 10 meter. Now size of electron is very less compared to, of course it's lesser than the size of the atom, it has to be, okay, because atom contains the electron, okay, not the other way around. So we can see that the size of atom is of the order of this, and the electron size is very less than compared to the size of the atom. So that means that the wavelength is of the order of 10 to the minus 10, which is the size of the atom. That means this wavelength is greater than the size of electron. So you have to note this thing, that this is a very important statement, note that if the de Broglie wavelength is comparable or larger than the size of the particle, then the wave nature of particle can be detected, okay, experimentally. So only when the whatever the object we are calculating for, like if you want to see a wave behavior, the wave behavior can only be detected experimentally only when the wavelength, the de Broglie wavelength, the calculation of the de Broglie wavelength gives us a result which is larger than the size of the particle, or of the order of the particle, or the order of the size of the particle. Then only we can see the wave nature of the particle. And this is a very it's very difficult to pinpoint which particles will show and which particles will not experimentally. It only depends on, we conduct diffraction experiments to see whether the given particle has a wave nature or not. Okay, so diffraction is a wave phenomenon. This is a purely wave phenomenon. Any particle showing this diffraction results, it definitely has a wave behavior. Okay, diffraction and as an interference is also a pure wave phenomena, because wave phenomena, when I say wave phenomena, that means it can be explained using wave theory only. All right. So now this question was asked in SU 2016, that the de Broglie wavelength of electrons and electronic charge, okay, accelerated through a potential difference of V is. So for this we'll look at the problem in detail. Okay, you can try it if you want to, but if you haven't done this type of problem, just look at the solution which I give you. If the potential difference between two plates is this is minus, this is plus. Now if you have a charged particle which is at rest in at this point, okay, and the distance between these two is d. These are two charged plates, and you have a charge here. There's a mass here, and there's an electric field between them. Okay, so the force on the charged particle will be force on particle will be QE, right? Right. So the force acting on this particle is QE, and it's along this direction. Okay. So what is the work done by the particle, the electric field, to move the particle from a distance dx? Work done by electric field. Okay. So the small work done is F dot dx, okay, equal to F dx. All right. So because the angle between them is the movement, the displacement is along the same direction as E, so the cos is 0 degree. So F dx. Okay. So that if you want to calculate the total work done to move the particle from this point to this point, will be the integration over dw, which is from 0 to d, and this is F dx. Okay, so if we integrate this thing, which we get is this is F into d. Okay, now this Q, F is what? Q into E, this is d. Okay, so this, we know that for a uniform field, the electric field is given by the potential difference between the plates and divided by the d. Okay, this is for uniform field. Okay, for uniform field. This is from the EMT, okay, electromagnetic theory. So if you substitute this here, so what we get is, we can write that V is equal to E into D. Okay, instead of ED we can place V. So the work done by the electric field is what? It is equal to QV. Now from work energy theorem, what we have is, from work energy theorem, what we have is the work done on the particle is equal to the change in its kinetic energy. The work done on the particle is equal to its kinetic energy. Okay, change in kinetic energy, change equal to change in its kinetic energy. Okay, so the work done, we can write mathematically that K E final, K E initial. The K, we are using abbreviation kinetic energy for K E for kinetic energy. So initially the kinetic energy is 0 because it was at rest, right? So the final kinetic energy becomes equal to the work done, alright, which is QV, sorry. So lambda is equal to h by p, and this h divided by 2m, this is kinetic energy final, alright, this is kinetic energy final. Now this is h by, this is root 2m, this is QB, alright. So what you do is, see, this is the result. You don't need to remember these things. It's very simple. Like you just had to instead of energy, we had to substitute the kinetic energy, which was equal to the work done. Okay, QV. Okay, this is the result. So if you have been given a potential difference, like for particle accelerated between a potential difference, this is the result. This is the way you calculate de Broglie wavelength. Okay, and if you put down the values for this is 6.626 into 10 power minus 34. Now divided by this mass is given to be this 9.1 into 10. It has the particle is the electron. Okay, 10 to the power minus 31 into the charge is I need to extend this thing. The charge is 1.6 into 10 to the power minus 19 coulomb into the potential difference. Okay, so these are all under the square root. Okay, so this gives you 1.5. This is V in nanometer. All right. So if you see the result, it matches with B option. So correct option is B. Correct option is B. So thank you for watching. Have a great day. If you find these lectures useful, then please like, subscribe, and share with your friends.